Imagine a star so massive that if it replaced our sun, it would swallow every planet up to Saturn. Sounds like an exaggeration. Well, get ready, because today you're going to meet the largest star ever discovered in the universe. And it makes our sun look like a marble. But what makes this star so special? How big is it really? And most importantly, is there a limit to how large stars can get? Stick around till the end, because the size comparison you're about to see will literally blow your mind. What's the biggest star in the universe? And why is it so ridiculously huge? And what even are stars, really? Things that want to be stars. To wrap our heads around this cosmic madness, we're starting with Earth. Not to learn anything deep right away, just to get a rough sense of scale. Because the smallest star-like things out there aren't stars at all. They're gas giants, massive planets like Jupiter, the heavyweight champ of our solar system. Jupiter is 11 times wider than Earth and weighs in at a whopping 317 times more mass. And fun fact, it's made of pretty much the same stuff as the sun, just way less of it. Now, on the road from planet to star, we run into a strange kind of celestial middle child, brown dwarfs. Basically, these are failed stars, cosmic underachievers that never quite made it to the big leagues. With masses between 13 and 90 Jupiters, they almost had enough oomph to ignite like real stars. But even if you slammed 90 Jupiters together, which, yes, would be awesome to watch, it still wouldn't be enough. And here's the twist. When you do pack in more mass, brown dwarfs don't get much bigger. Instead, they just get denser. Their insides squeeze so tightly that some light fusion can spark, enough for them to glow faintly. So really, brown dwarfs are weird glowing gas giants that don't fully belong anywhere. Not quite planets, not quite stars. Just a bit lost in the cosmic in-between. But we're here to talk about stars, real stars, not cosmic almosts or wannabes. So let's move on. Meet the main sequence stars. These are the stars that made it. When a giant ball of gas gathers enough mass, something incredible happens. Its core becomes so hot and so dense that nuclear fusion kicks in. Hydrogen atoms start fusing into helium, releasing a mind-blowing amount of energy. Stars that can do this earn their place on what's called the main sequence. And here's where it gets wild. The more massive a main sequence star is, the hotter it burns, the brighter it shines, and the faster it lives and dies. Once it runs out of hydrogen, a star can expand to hundreds of thousands of times its original size. But these giant phases don't last long. So in this video, we'll be comparing stars in totally different life stages. That doesn't make them any less awesome. But it's worth remembering, we're kind of comparing babies to full-grown adults. Now let's rewind a bit to the very beginning of what counts as a real star, the red dwarfs. These tiny stars are just barely massive enough, about 100 times the mass of Jupiter, to pull off hydrogen fusion. Because they're small, they're not super hot and don't shine very brightly. But here's the cool part. Red dwarfs are the only stars that don't puff up when they die. They just kind of fade away, and they're everywhere. In fact, red dwarfs are the most common type of star in the universe because they burn their fuel incredibly slowly, lasting up to 10 trillion years. That's 1,000 times longer than our sun's entire life. Let's talk about the age of the universe, because in cosmic terms, that matters. For instance, one of the closest stars to Earth is a red dwarf called Barnard's star. But it's so faint you can't see it without a telescope. We actually made an entire video on red dwarfs, so check it out if you want to dive deeper. Now, moving up the ladder, let's talk about stars like our sun. Saying the sun dominates the solar system honestly doesn't do it justice. It accounts for a whopping 99.86% of all the mass in our entire solar system. It burns much hotter and brighter than red dwarfs, which means it uses up its fuel faster, living only about 10 billion years. It's about 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter and gives it double the surface temperature. So, what happens if we go even bigger? Well, in main sequence stars, even small increases in mass create massive jumps in brightness. Take Sirius, the brightest star in our night sky. It's twice the sun's mass with a radius 1.7 times larger. But its surface blazes at nearly 10,000 degrees Celsius, making it shine 25 times brighter than the sun. That intense burn comes at a cost. Sirius will only live about 2.5 billion years, a quarter of the sun's lifespan. Now imagine stars with 10 times the sun's mass. These monsters can reach surface temperatures of 25,000 degrees Celsius. Beta Centauri, for example, has 2 of these colossal stars, each pumping out 20,000 times the sun's power. All of that energy from something just 13 times bigger. But there's a trade-off. They'll burn out in just 20 million years. Entire generations of massive blue stars can be born, live, and die in the same amount of time it takes the sun to complete a single orbit around the galaxy. So, is that the rule? The more massive a star is, the bigger it gets? Well, not exactly. Meet R136A1, the most massive star we know. It clocks in at a jaw-dropping 315 times the mass of the sun and shines nearly 9 million times brighter. But here's the twist. Despite its insane power, it's only about 30 times the sun's size. This star is so extreme, so barely held together by its own gravity, that it sheds an unbelievable 321 billion tons of material every single second through intense stellar winds. Stars like R136A1 are incredibly rare because they sort of cheat the rules of how stars usually form. When these ultra-massive stars are born, they burn so hot and bright that they actually blow away any extra gas that could have made them even larger. So, the natural mass limit for a star sits around 150 solar masses. Stars like R136A1 likely formed when several already massive stars merged together in densely packed star-forming regions. And once they're born, they tear through their core hydrogen in just a few million years, burning fast and dying young. So what if we want to go even bigger? Here's the twist. You don't add more mass. To make the largest stars in the universe, you actually have to kill them. That's where red giants come in. When a main sequence star starts running low on hydrogen in its core, the core collapses, getting hotter and denser. This triggers faster, hotter fusion, pushing outwards and causing the star's outer layers to expand massively. That's when stars truly become giants. Take a star like Gay Crux, for example. It's only about 30% more massive than the sun, but it has already ballooned to nearly 84 times the sun's radius. And that's nothing compared to what's coming for our own sun. When it reaches the final stage of its life, it'll swell up even more, growing to almost 200 times its current size. In that fiery finale, it'll engulf the inner planets. Pretty wild, right? But as impressive as that sounds, it's time to meet the true giants of the universe, the hypergiants. These are the final bloated stages of the most massive stars out there. Their enormous surface areas blast out mind-bending amounts of light. They're so big, they're basically tearing themselves apart. Gravity just isn't strong enough at the surface to hold everything together, and their hot mass is blown away in massive, violent, stellar winds. One extreme case is the Pistol Star. It's about 25 times the mass of the Sun, but nearly 300 times its radius. It's a blue hypergiant, named for its intense, energetic, blue glow. It's hard to pin down exactly how long a star like this will live, but odds are it's only a few million years. And just when you think stars can't get any larger, enter the yellow hypergiants. The most famous is Rho Cassiopeiae, a star so bright you can actually see it with the naked eye, even though it's thousands of light years away. It has about 40 times the Sun's mass and a radius nearly 500 times larger. It also outshines our Sun by 500,000 times. If Earth were as close to Rho Cassiopeiae as we are to the Sun, we'd be inside it and very, very dead. Hypergiants are incredibly rare. We've only confirmed around 15 of them so far. This suggests they might just be a short-lived in-between phase as stars grow or shrink while transitioning through different stages of hyperness. But when it comes to red hypergiants, we've reached the most extreme known stars in the universe, and probably the biggest ones that can even exist. So, who wins this mind-blowing size competition? Honestly, we're not totally sure. Red hypergiants are super bright and incredibly far away, which makes measuring them really tricky. Even the tiniest uncertainty in our data creates massive differences in size estimates, and it gets worse. Red hypergiants are so unstable and bloated, they're basically tearing themselves apart, which only makes them even harder to study. As our technology improves and we gather more data, our understanding of the largest star will keep changing. Right now, one of the top contenders is Stephenson 2-18. It likely started off as a main sequence star several dozen times the Sun's mass, but it has already lost about half of that over time. While most red hypergiants are around 1,500 times the Sun's radius, Stephenson 2-18 is currently estimated to be around 2,150 times larger, and it shines with nearly 500,000 times the Sun's power. When you compare that to our Sun, it's like putting a grain of dust next to a beach ball the size of a planet. The truth is, our brains just aren't built to comprehend size on this kind of cosmic scale. Now, let's put this into perspective. Even if you could travel at light speed, it would take you 8.7 hours to make just one trip around the largest star. Meanwhile, the fastest plane on Earth would take about 500 years to make the same journey, if it could even survive. This star is so massive, it would stretch all the way out to Saturn's orbit. And as it continues to evolve, it will likely shed even more mass and shrink down, entering another phase as a hotter, even more extreme hypergiant. During this stage, it will start collecting heavier elements in its core, but its grand finale is nothing short of spectacular. It will eventually explode in a core collapse supernova sending its gas and energy back into the galaxy, creating new elements and fueling the next generation of stars and planets. After the supernova, the gas and elements released will drift through space, eventually coming together to form the next generation of stars, from tiny red dwarfs to massive hypergiants. This cycle of birth and death continues, lighting up our universe in an endless dance of creation. Now, let's take this journey one more time. But this time, let's do it without the talking. The universe is vast and there are many extraordinary things out there waiting to be discovered. And so, we continue our journey through the vast and mysterious universe, where stars are born, live, and explode, giving rise to new generations of stars and eventually new worlds. This cycle of birth and death is what keeps the light of the universe burning, fueling creation and destruction in an infinite and fascinating rhythm. Now, imagine if you could apply this same cycle of transformation to your brain. What if you could accelerate your mind's power, unlocking a potential you didn't even know you had? What could you achieve with a sharper, more creative, and more focused mind? Introducing our exclusive digital product, designed to transform the way your brain functions, accelerate your learning ability, boost your memory, and become more productive in a simple and effective way. Imagine what you could accomplish with that level of mental performance. And here's the big offer. For a limited time, you can access our proven method with a special discount, along with incredible bonuses that will amplify your results. Don't miss this unique opportunity to change your life. Click the link below and start your journey to unlock the full power of your brain right now.